Good afternoon to everyone. Welcome to the session of statistics of the National Meeting of the Mathematical Portuguese Society. So I would like to thank the four speakers of this session for accepting the invitation to give a talk. Thank you very much. And I also thank the audience for attending the session. Okay, so our first speaker is Miguel de Carvalho from the School of Mathematics of the University of Edinburgh, and we will talk about regression type analysis for black swan events. Thank you very much, Miguel.
Thank you so much, Anna, for the introduction, and thank you also to the organizers for this wonderful meeting. So prior to getting started, I would like to partition into buzzwords the title of today's talk. So there will be ideas related with regression analysis, and regression is a mainstay of statistical modeling. And there will also be ideas on black swan events. Black swan events were popularized by Nassim Taleb, and they are just another way of describing extreme events, that is, events that are very unlikely, but whenever they happen, they lead to catastrophic consequences, such as an earthquake, a stock market crash, wildfires, among other events. So there is a branch of statistics known as statistics of extremes, or as extreme value theory, that is just devoted to the study of these events. And in today's talk, I'll be having a look into an open problem on that field. And the idea is how to devise a regression model for where you can have a response as well as a covariate that could be potentially extreme events. I'd like to acknowledge that this is joint work with Alina Kumukova, who is my PhD student, as well as with my colleague Gonçalo dos Reis. Okay, so let's get started. So in terms of the goal is really there's a covariate, which is a p-dimensional covariate, but it is a special type of covariate. It's not just a standard covariate. The covariate is in itself a block maxima, and there's a block maxima response. So it's a regression type of idea where we would like to predict the response by using information from this input, this covariate. And the question really is how to take into account the effects of covariates on an extreme value to a certain extent. Somehow, because there was already some models that were developed to this idea on really trying to explain a variable that is extreme given another covariate, and this has been explored in the literature of statistics of extremes. And these are the so-called models for non-stationary univariate extremes. And there's a few more references that I can mention in here, even some references from the remainder speakers in today's talk. This is just a snapshot of work that has been developed along this direction. Unfortunately, though, these methodologies that have been proposed earlier, they are not suitable, they are not appropriate for modeling also extreme covariates. So, and the goal really here is how can we actually try to explain a response which might be extreme, also keeping in mind that your covariable will also be extreme as well. And there's other approaches that I'd like to mention as well in terms of conditional approaches for multivariate extremes that do have some points and some links with what I'll be discussing in here today, particularly the works that I mentioned there. Okay, so now I want to switch gears and tell you about what is our take, what is our approach in terms of thinking about this problem. And that is mainly based on this idea of what we call the regression manifold. What is a regression manifold? So let's start with data. And our data are essentially just the following pairs, S and zeta, where essentially just start thinking about S as a response and zeta as a covariate. But these covariates and these responses, they are assumed to be independent vectors with unit Fréchet distribution, whose distribution function is given by this. So unit Fréchet distribution is just a canonical extreme value distribution. So this is, I'm assuming this without loss of generality, as we can always convert the data into this scale. Okay, let me introduce then some notation. Component-wise maxima are defined in this way. So they are just the maxima of the corresponding variables, in particular for all the variables, including covariates, as well as in terms of the corresponding response. And this is background still, and there's a well-known result that was proved by Lawrence Dunn and Sidney Resnick a long time ago that shows that the standardized sequences will converge in distribution. If they do converge, they will converge towards a distribution function G, whose expression looks like this, and whose parameter H is known as the angular measure. So the angular measure is what? Is just a probability measure defined over the d-1 dimensional simplex. And in terms of our setup, I'll be referring to D as the number of dimensions, but of course, keep in mind that P will be used for number of covariates. So there's one response and there are P covariates, so dimension will be equal to P plus 1. And this parameter of interest in here is a parameter that needs to obey a constraint. So it's not just any standard probability measure over the unit simplex. It still needs to obey the following moment constraint in here. So in other words, its mean needs to be centered on the barycenter of the simplex. Okay, so this is background. So let me now move into reminding you the goal. The goal is to relate block maxima response and block maxima covariate. And in terms of the definition that we propose, the parameter of interest in here will be what we'll call a regression manifold. And the regression manifold is a family of regression lines, in the sense that we define L to be this family LQ, where essentially this LQ is just a family of conditional quantiles with the family being indexed by Q, with Q being the corresponding quantile, and where G of y given X is just a conditional multivariate extreme value distribution function, which is just obtained by actually conditioning the previous distribution function I've introduced earlier, where I mentioned the result by Dian and Resnick. Okay, so this is a family. This is a family, and there are ideas in here that will certainly be similar but different from quantile regression, in the sense that in here we build the family of regression lines via the joint distribution function, rather than specifying a functional form between the response and the covariate. Let's see this, how it looks like in a parametric model. So there's a famous parametric model known as the logistic model, whose functional form is given by this for the joint distribution function. And the corresponding regression manifold is what you see here on the right. So where actually this family of lines is as the following expression in here, which depends on this function, which is the so-called Lambert W function. If you're not familiar with the Lambert W function, think just about it as an extension of the logarithm function, in the sense that it is the inverse of this function in here. So if you didn't add in here this W, essentially this would be actually the logarithm function. Okay, let's see how it looks like. So this is for alpha equal to 0. That's essentially for the case of perfect dependence. And let's see how it would look like as you start decreasing actually your level of dependence. You see that you start with something that keeps putting in more and more mass here close to Q equal to 0. Okay, so this would be it. You start anticipating what would be the structure actually of this object as a function of the level of dependence. So this would be the way that the regression manifold would behave as a function of dependence. Okay. So there's a property that I would like to mention in here. You might argue that, okay, but these are conditional quantiles essentially. So yes, so that means that they will obey just standard properties of conditional quantiles. So, but beyond that, there's a property that can be shown that regression manifolds, at least in 2 dimensions, obey. That is, when you have one single covariate. And that property is the so-called, what we call monotonicity of the regression manifold. And essentially what it implies is that, provided that your conditional bivariate extreme value distribution, your G of y given X, is jointly continuously differentiable and strictly increasing in Y for any given X, then that implies that the regression lines, that LQ that I've introduced earlier, will be actually non-decreasing for all Q over the unit interval. So the proof is just a consequence of this theorem that was established by Guillem, and that combined with the implicit function theorem. Okay, and this will let's see now in terms of what we can see in terms of this. We'll see some charts where this property will be verified. So just keep in mind that as a function of x for all fixed q, this will essentially just be non-decreasing. Okay, one thing is introducing regression manifolds. The other question is, how do we learn about regression manifolds from data? And this is what I'd like to address next. Okay, now what we do is the following. We resort to Bayes' theorem. So we resort to a Bayesian inference mechanism based on Bayes' theorem in order to learn about regression manifolds from data. The way that we do this is actually, first, we put a prior on H that I've mentioned earlier, the angular measure. So we put a prior on the space of angular measures. And given that, so after that, we induce a prior on the space of all regression manifolds via this prior that we set up on H. The idea is as follows. So the prior that we consider is essentially based on the so-called random Bernstein polynomials. And random Bernstein polynomials, they are essentially what? They are a mixture, a special type of mixture of beta distributions. So this would be the Dirichlet density, and where these guys in here would essentially be just weights in there. And these weights need to obey two constraints, a normalization and a moment constraint. Okay, what then this induces, as I mentioned, is a prior on the space of regression manifold. So by plugging in this H on the corresponding conditional bivariate extreme value distribution, you can actually induce then just a prior on the space of regression manifolds as well. And then inference is via a component-wise adaptive Gibbs sampler. So an algorithm then for actually implementing this. Okay, this is just a proof of concept. So this is for a bivariate user Rice model whose distribution function looks like this. And you can see on the left the true, and on the right you see the estimated regression manifold with these data in here, which is overlaid on one of the faces of the box, being the artificial simulated data that we've used for learning about this curve in here. Okay, so this is a proof of concept. In the paper we conduct, of course, Monte Carlo simulation studies, but this is just to show that it works. And in this case, the corresponding regression lines, this is for q equal to 0.5. So this would be like a conditional median, would look like this. And again, this would be the simulated data that we've used for this simulation, whereas in here on the right, you see the corresponding conditional quantiles. But this is with artificial data. I'll skip this, keeping the time in mind. The bottom line is that we can still apply this for if you have more covariates, but you need to resort to an extension. So I'll skip this and I'll move to the application to close. Okay, so what we're using this method now is to address and to examine what is the spillover in terms of extreme losses between the New York Stock Exchange as well as the NASDAQ. Okay, so you would like to see if one market plummets, what happens to the other market? What's the degree of synchronization? And these are two of the leading and major stock markets, and this would be their corresponding indices in here in US dollars over the period that is mentioned in here. Of course, you start seeing that peaks go hand in hand. You start also seeing that whenever you see some sudden changes, they do tend to go hand in hand together, including in here, for example, this one, which is related with COVID-19. Okay, so let's see about how to learn implementing this to learn about the regression manifold in practice. So this in here is the corresponding regression manifold. In here it's not converted to unit Freshian margins, whereas in here you see that it is converted into unit Freshian margins. Since this is an inverse manifold, let's have a look at cross sections in order to get a better feeling for what this is actually telling us about. So these are just cross sections of the chart I was presenting earlier, but where you actually fix these three quantiles in here, so 0, 1, 0, 5, and 0, 9. So, and what you start seeing in here, for example, in terms of this line in here, this line is telling you that given losses on the NASDAQ, so you start getting predictions in terms of losses in terms of New York Stock Exchange, but in a way that it actually extends beyond your observed losses into the joint tail of your distribution. And this is essentially telling you, this line is telling you that only 50% of your data would actually should be along this line for a loss on the NASDAQ, say, of 5%. Let's see this in a table in order to make more sense out of this. Okay, suppose you see a loss on the NASDAQ of a 3% loss on the NASDAQ today. So, and over this week. And you would like to then see what does that imply in terms of losses on the New York Stock Exchange. And what you can see from this table is that only in 5% of the times you would be losing actually more than 3.3% in terms of the New York Stock Exchange. Same thing in here, if you see a loss of 2% in terms of the NASDAQ, only in 5% of the times you will be expecting to exceed a loss of 2.5% on the New York Stock Exchange. So this would be the sort of take-home message that you could get from this sort of analysis. I want to close. We proposed a model that links block maxima response and block maxima covariates. We learn about this model from data using random Bernstein polynomials, and I applied these to data from stock markets. So thank you. I would be happy to take questions. Thank you so much.
Okay, thank you very much, Miguel, for this very interesting presentation. So now we have some time for questions or comments. So if you have questions or comments, please write in on the Q&A button that you have on the bottom of your screen, please. If the other speakers want to make questions, they can do it orally. Okay.
Yeah, maybe I have a question on the last two type methods. A comment more than a question. So like we are trying to do some let's say forecast of nonlinear systems like the Lorentz attractor. And we see that indeed for this physical system where we have nonlinear dynamics, it's very interesting to use these methods where we can have covariates that are exactly zero at a certain point. So because the lasso gives a penalty and can allow zero coefficient. So I think this idea of using statistics to see what are the relevant covariates is really good, and it's something that is not yet so much explored right now, and maybe also in the field of extreme events can be a good idea. What is your opinion about that?
Okay, thank you so much. I think that's actually a very, very interesting point to bring to the discussion. So in terms of, I see two points to comment on related with that. One is in terms of lasso type models in terms of this setup. And one way to go would be, of course, to penalize some of the dimensions in the way that would be your way to induce shrinkage, to induce regularization. And of course, one way to go, I think, and this is one paper that my student is also exploring at the moment. It's the idea is simply to, rather than starting with models such as random Bernstein polynomial, starting actually with a parametric model, and on that parametric model, say a logistic model, and then actually to penalize actually some of the dimensions there. We're at the stage, this is still ongoing work, but this is definitely something that I would see more work coming on here, because I don't think there's more to do definitely in terms of that problem. And it also relates with the problem of dimension reduction in multivariate extremes as well. a second point that I think that your comment brings to the discussion is also what is regression as well, and in terms of what we're covering in here. So in terms of the idea, and this is why we call it a regression type model, the idea is really to actually think about regression just as a model where you actually have a covariate and you actually have a response. And then the idea is to have a joint distribution and to actually model the conditional quantiles via that joint distribution. So there is no need to specify ex ante any specification that relates your variables, such as you would do, for example, in terms of quantile regression or in terms of standard linear regression. I think though this is one way to think of that. Perhaps some people would argue that, okay, but that's beyond regression, and that is somehow why we're calling it also regression type. So thank you. I think that's a very good comment.
Okay, are there more questions or comments? I think we have a question on Q&A. So could there be different priors depending on the specific application?
Good, excellent question. So since we're only using setting one prior in here, it raises the question in terms of what is how sensible is this prior? And this prior is known to be extremely flexible. So there's a standard theorem in analysis that can actually get us to characterize the flexibility of Bernstein polynomials. So Bernstein polynomials are known to be dense on the space of all distribution functions, and this prior is extremely flexible if we allow the number of components to go to infinity. So yet, of course, the related question is, if I'm actually a Bayesian who would like to elicit prior knowledge from an expert using this model, how would I do that? And I think that would be challenging in all honesty, because there's many parameters involved. I think that would be a tricky part in terms of how to take on board that knowledge. So yes, yes, it's a good question. Thank you.
Okay, more questions? So if there are no more questions, I think we can move on to the second talk. So our second speaker is David Miranda from the Laboratory for Sciences of Climate and Environment of the University of Paris-Saclay, and we will talk about statistical physics of geophysical extreme events. Thank you very much, David.
Thank you very much for the invitation, and it's always a pleasure to give a talk at the seminar of at the Conference of Mathematics, although I'm a physicist, and so there will be little mathematics in this talk. But I think the important thing is maybe to make the connection between these two words. That is also what I tried to do in the first 10 years of my research career, counting on the PhD thesis. And in fact, this connection between statistics and mathematics and physics allow to build framework, for example, to study geophysical extreme events. And why it's that? The fact is that in physics, we have already the world of statistical physics and the world of dynamical systems. So these two disciplines in physics are a bit of separate, because in statistical physics, what we have is small particles, and then we try to find the collective behavior of these particles and try to write distributions or steady states, steady distribution to describe them. Whereas in dynamical system, we try to find the trajectory, so the evolution of this any system. But normally, when we are able to do so, we have to write an equation for each of the variables of the system. And so immediately for geophysical flow, it becomes very complex, because we have to study an incredible number of small entities, such as, for example, the fluid particles, and then use Navier-Stokes equation. Okay, so where is the problem? Because you say, well, let's use the Navier-Stokes equation then. Well, Navier-Stokes equation are difficult to simulate and very expensive. And there is an important fundamental challenge, that is the fact that in complex systems, and in particular in climate, the extreme events are not at the scale of the particles, so are not at the scales of the where we can define fluid particles, and not even at the scale of the radius of the Earth. What we want to study in climatology, and this is my field of research, are the extreme events that have some intermediate radius between the integral scale of the system and the scale of dissipation, okay? So this is problematic because we have this kind of object that you see here in this example. And this is an example taken from Meteo France, and like this is the heat waves in 2019, where we reached more than 40 degrees in Toulouse and 43 degrees in Montpellier. And as you can see from the scale that basically is separating the warm air, here air show in this slide, from the fresh air, the cold air here in the Atlantic, we have some specific scale that is the scale of the anticyclone, and this scale does not correspond to the smallest or the largest scale of the system. It's just in between. And there are other phenomena that are like this. For example, if you can think of a thunderstorm, well, a thunderstorm has a very well-defined scale of some tens of kilometers. So the question is, how do we study that? Okay, so when we want to study these extreme events in climate, what is the motivation? It's not just to see and to say whether they will happen next week, because this is the field of meteorology for the climatologists like me. The question is a question of statistics indeed. So it's about the changes in frequency with different climates that we can build using different emission scenario. Then we can ask how persistent are these events and how persistent they could be in the future. And also, if we want to boil down this to dynamical system point of view, whether they are more or less predictable. So all these questions can be answered after we select first the event. And to define the event in climate science is also a question that is important for statisticians. So I want to draw your attention on this chart that is proposing a certain way to select the heat wave. Here it's a marine heat wave. So the heat waves in climatology are not just peak over threshold, but they are peak over threshold with a condition of clustering. Okay. So for example, if we take the heat wave for Meteo France, is at least 3 consecutive days with the mean daily temperature above a certain quantile. But so as you can see in this graph, we have that at the beginning we have some heat spikes, and then we have a heat wave, but the heat spikes are not a heat wave just because they don't last long enough. So there is already a question of which definition to apply, where you can work on if you're interested. We don't have many ideas on that, and it's a huge problem in the climate community. So this, the first message I want to give in this talk is, please help us with this. I'm sure you have lots of nice tools to make things more properly. And the second thing is this kind of animation. I hope you can see the animation. It's not important the details, but just see this structure moving. Is the choice of the observable, okay? So if we want to look at heat waves, and this goes to the problem that Miguel was raising before, which covariate, which observable we have to take. So here in this map, there is the sea level pressure, and this is the isolines, and there are the geopotential height. The geopotential height is the height in meters where we cross the 500 hectopascal isobar somewhere in the troposphere. And this is about 5,000 meters, okay? So as you can see, both these observable can trace the dynamics. So we have a problem also on the choice on the observable. And what we do to kind of propose a solution to this problem, we use dynamical system theory and we combine it to extreme value theory. So we consider that we have some events in phase space, okay, for the current climate simulation with the current content of greenhouse gases. We look the recurrences of this, so we minimize the distances in phase space with respect to a chosen trajectory. So these trajectories, for example, where you see we have this variable that I call geopotential height in all the 1000 locations that are our grid points on the map. And so this approach of following the recurrences of dynamical system is one of the main contributors is the couple Freitas. Then we have other mathematicians. Now it's more than 10 years of successful application. So these techniques now is very widespread, and there are colleagues in oceanography, colleagues in seismology that use these techniques to study the extreme events in different fields of science. Why? Because it allows to boil down the dimensionality, to somehow remove the curse of dimensionality just by looking at the recurrences. And why it's that? I repeat this. So what happens in the future? We look at the shape of this ball, okay, that is just defined by the recurrences. And if the shapes, the parameters that can define this ball that are related to the extreme value distribution, the generalized Pareto distribution, change, then we have our climate change for the extreme event. So if you understand this point, now all the mathematics will be like trivial for you. And we could define actually 3 indicators that are the change in the size of this ball. Okay, this will be the change in frequency, because if the events in the future will be farther from my target point, but then it means that they will be less frequent. Then I have a change in the time inside the ball, so the local persistence, that will mean the changes in persistence, and the orientation of the ball. This will give me the changes in dimension and therefore in predictability. So now how all this link with the extreme value theory? So this I take, this goes back to the paper of 2008 by Freitas and Freitas, and it's basically a very nice idea, a very clever idea of looking at the evolution of the system. So here I'm representing the Lorentz attractor, but just to show you that time is in colors. And so in chaotic attractors, we have mixing. So we have the color mixes, and we can use the independence conditions that we have normally in statistics, okay? So when we look at the recurrences around a ball centered around this point zeta, and we apply a minus logarithmic weight to the distances between this point and all the trajectory, we get an observable that is one-dimensional, because the distance squeeze of everything in just this univariate time series, and the minus sends the minima in the maxima. Once we have this distribution xm of x, it's the distribution of minima of the distances. We know already that is a Pareto distribution, and actually, if the system is chaotic, is exactly the exponential member of the Pareto distribution, which is even better, because we can get the interesting parameter just by fitting, for example, by measuring the average of the exceedances. This will give us lambda, okay, as you know, and this will be an estimate of the dimension. So we have already, the first estimation is of the predictability is just obtained by looking at the scale parameter, or as the only parameter actually to have in the exponential distribution, or the scale parameter of the Pareto distribution. So with this in mind, we have done several things, for example, characterizing the weather regimes. So the dimension, I forgot to say that if we look instead at the extremal index of this problem, then of course this will give us the persistence, okay? I don't have to explain you because you all know this. So when we look, for example, for daily maps okay, from 1948 to 2015 of this kind of observable, I go back, sorry, but this kind of maps, we set this as a target. We measure the distances from these maps on all the data set, and we perform these analysis. We can have for each of these maps a dimension and the persistence, okay, by doing recursively applying recursively this formula. What we can do, we don't have the attractor like the Lorentz attractor, but we can do a scatter plot of dimension and predictability. So the extremal index versus the 1 over lambda of the exponential distribution, and the extremes, the minima and the maxima of this object tell us the nature of the most extreme fields that we can have in the atmospheric circulations. And guess what? Just without doing non-hypothesis on what are these fields, we find what the meteorologists call the weather regimes. So this is one of the main results that we obtained, and I won't lose that much time to explain the rest, but then we can apply this procedure to climate models. We can do it when we have the thermodynamic trend, when we don't have the thermodynamic trend, in historical simulation, in simulation with greenhouse gases scenarios. Okay, so this that I call here RCP 4.5 is a scenarios of intermediate greenhouse gases emission, and RCP 8.5 is the business as usual scenario. And we can look at the changes of this indicator for different class of extreme events. So I select some part of extremes and I look what happens. And I won't go anyway in the details here again. I just show you what happens for the heat waves. So the heat waves, for example, if we ask about the 2003 heat waves, can it become more predictable in the future, more persistent, less or more probable? Well, it depends on the scenario that we consider. But you see that for different heat waves, we have different magnitude of changes, but very nicely, even here without any hypothesis, just by applying this indicator, we have that the changes are consistent with different extreme events. So this is very nice. And of course, as you can imagine, we get that the heat waves increase in the future, the cold spells decrease, and you see already that for the cold spells here, the results are a bit different if the events that we consider is different. So I won't go into the details of all of this. It's just to say that we have a bridge between the statistics and the physics. This bridge works at any scales now, because the way this theory is constructed, we understand that we can use it to study heat waves, cold spells, storms. What we have to find, what Miguel was saying before, is we have to find the good observable. And when we do, for example, this scatter plot of these properties of extreme value distribution, by looking at the fields that emerge as extreme, we can identify from a physical point of view the good observable. So we have now a tool that is ready to do what we call attribution of extreme events. So at least for the atmospheric circulation, and where you can help. Well, you can help, for example, on the multivariate aspects, because I said I always talk about one single observable here. So what happens if we now consider, for example, a bivariate version of all of this, where we have, for example, temperature field and circulation field, pressure fields, and things are a bit more complicated. What if we add 3 fields and so on? There are many theoretical and statistical aspects to still investigate. And of course, I hope this motivates some further discussion with you. So here is a list of the reference on our physical side. There are lots of reference from Anna Cristina side from the mathematical point of view. And I thank you very much for your attention, and I'm happy to take any question on this or whatever question you may have.
Thank you very much, David, for this very nice talk. So are there questions or comments? Yes, Miguel, please.
It's more a curiosity. Thank you very much for your talk. In terms of the circulation patterns, if there are circulation patterns that are really beyond what we've seen thus far, would it be possible to extrapolate beyond observed circulation patterns?
Yes, yes, indeed. In fact, there is an interesting thing of this diagram that I didn't say here, but we have it running every day. This is every day we run this dynamical system approach for the circulation that is just coming from the meteorological center to our laptop, our computer, and you know the Filomena storm this year in Spain. So we had a point here. I don't know if you see my pointer. It was the point with the higher dimension and the lowest persistence, because the extremal index is defined on 1 over the persistence. So we can see also the creation of this new pattern. And I think this is very interesting because we have also an indicator to see, is this event typical in our system or is this unprecedented event? And so, for example, now the question is about the Canadian heat wave. Is this an event of our attractor in some sense or not? So the things, we didn't do the analysis, but we see from the statistical indicator that's also very interesting for you. The temperature was 5 sigma away from the mean. So I don't know if you're used to see a 5 sigma event in your, this is even beyond extreme value theory. So it's 5 sigma with respect to, for example, daily temperature measured from 1948 to now. So it's a lot. So we have some diagnostics to see if these events are from this world or they come from another world, which in dynamical system theory means that so you cannot extrapolate your asymptotic distribution, because at a certain point there is another state that is not from the same distribution. There is it's like a double well potential. There is another state, maybe a persistent state or a heat wave state, that we cannot model unless we know what is the dynamics that is creating this state.
Thank you.
You're welcome.
Okay, if not, so thank you again, David.
Thank you very much.
Thank you. Now
we have a question. I think we have a question in
yes, we have a question now. So,
by George. Hi, George.
So George asks, you also have some synchronization results by taking 2 orbits and then taking the distance between them. Maybe there is a connection with Miguel's work as well through that direction?
Indeed, yes. This is one thing also we looked with Sandro, actually, when we look at how to define using your tools the correlation dimensions. So we take then 2 trajectory and we see when they stick together. But actually what we can do also is taking 2 observables and see when they stick together. We can do lots of things, and we didn't exploit this too much. So we should maybe go into this direction. Because what we do here that I didn't explain well is that if we have several days from an observation of an extreme event, we take all this bunch of trajectory, we put it in the climate simulation like it was observed in the climate, and then we measure the recurrences there, okay? So it's like we do some kind of transplantation of the observation into the climate simulation. We do what we call bias correction, that is like we avoid that this is rejected by the destination trajectory, so they have to belong to the same world, and then we do the analysis. But actually we could do it dynamically, and this is very interesting, and yeah, we can discuss further about that.
Okay, thank you again. So
thanks a lot.
Thank you. We can move on to the third talk. So our third speaker is Mafalda Viana from the Institute of Biodiversity, Animal Health and Comparative Medicine from the University of Glasgow, and she will talk about Bayesian state space models to optimize malaria vector control, quantifying the impacts on mosquito population dynamics and life story. Thank you very much, Mafalda.
Thank you. Can you see my screen well?
Not yet.
Can you see my screen?
Not yet. No, no.
Oh.
Yes, now we see it.
Excellent.
Thank you.
Good afternoon, and I would like to start by thanking Anna Christina for the invitation to share my research with you. Today I will be talking about Bayesian state space models and how we can use them to improve public health decision making, in particular how to optimize vector control strategies. As you probably know, malaria is a disease that's transmitted by mosquitoes, and it's the vector-borne disease that has the highest mortality worldwide, with more than 200 million cases every year and almost 500,000 deaths, 90% of which occurring in sub-Saharan Africa. And there is currently no effective vaccine against malaria. So vector control, so the killing of the mosquitoes, is the most widespread and useful tool that there is, and it has been incredibly successful. So as you can see from these maps here, malaria prevalence has reduced about 50% between 2000 and 2015, which is amazing. And this reduction has been attributed mostly to vector control strategies. So we can see here in this right plot of malaria adverted cases over time, and the colors are the cases adverted by the three most used tools, and the green, which is insecticide treated bed nets, have actually reduced malaria cases by about 68%. So this has been an amazing progress, but the problem is that despite this success, in the last few years, malaria started to increase again. And the reason for this is that the mosquitoes are changing in ways that diminish the effectiveness of these vector control strategies. So mosquitoes are developing behavioral and insecticide resistance that no longer kills them when they are exposed to certain interventions. So we really need to find new solutions for vector control that are faster and they are sustained in the long term. And there are many options being developed, from new insecticides to gene drive approaches, and some to be used in isolation, some in combination. But the problem that we currently have is that there's no good way to determining whether a specific intervention is working as it should or as we anticipate it to work. So most often we have an intervention and then we can see whether the vector population increased or not. But with this approach, we don't know how this final outcome is occurring. So we don't know what the mechanism driving it is. And this means that it's very difficult to effectively combining interventions or finding ways to improve those interventions. So we've been trying to get at these hidden processes to understand the why by combining mosquito surveillance data that is routinely collected with interventions with population dynamics models constructed under a state space framework. So the question I pose today really is, can state space population models reveal those hidden processes driving the impact of vector control strategies? Or in other words, can they tell us whether interventions are working as anticipated, and if not, why? And I'm going to be talking about this in the context of mosquito surveillance data that was collected during a clinical trial implemented in Burkina Faso. And these maps here are just to kind of locate you. Burkina is a West African country surrounded by Ghana, Mali, Benin, and so on. And the trial took place in the south of Burkina Faso here, where the star is. in around what were defined as 40 clusters, represented here by the blue dots. So this trial was a stepwise randomized clinical trial implemented to compare two different types, to the efficacy of two different types of net. The standard long-lasting insecticide-treated bed net, the LLIN, which has a single ingredient, which is the chemical pyrethroid, which was developed to reduce adult mosquito survival. And the newer nets, the PPF LLIN nets, which has two active ingredients. So in addition to the pyrethroid that exists in the current LLIN, it has a second called pyroproxyfen, which is a juvenile hormone growth regulator that in the lab has been shown to impact reproduction, but could also impact larval development or pupation. So in the field, we don't really know the impact or if it impacts at all. So this trial enrolled around 80 villages that were put together as 40 clusters. And all of the clusters, or all houses inside the clusters to start with, were given the standard LLIN bed net. And then as time went by, in a kind of randomized fashion, you can see here in this table, the different clusters were given the new net, the PPF net. But importantly, throughout the 2 years of the trial, monthly vector collections were done in multiple houses in each of the clusters. And this is the data that we have and that we will use to assess the impact of the PPF nets on the vector population. So this is just to give you an idea of the resulting time series that we have. This is the adult collection. So in blue, you have the average mosquito abundance per trap over time with the LLINs, and then in yellow with the new nets. And so the question is, how do these PPF nets impact mosquito population dynamics and demography? So what we did was we fit this data to a state structure population model built under a state space approach. So the SMM has a biological process, which we define as a population model based on weekly mosquito life cycle. So the larval that survives takes 14 days to develop into this juvenile form. And the juveniles, they haven't laid eggs yet, but after the first meal, they enter a cycle of feeding and of laying eggs and blood feeding, laying eggs and blood feeding, and so on. And so a few things to note about this model is that in orange here, we see the critical life history parameters that we are interested in and that we find through a series of equations, of course. So the survivals are binomial processes, fecundity are Poisson processes, and so on. So how the mosquitoes flow through these rates describes the population dynamics, or in other words, the mechanism behind population size. So in addition to the baseline values of each of these life history parameters, so we linearize them, and these rates are driven by several ecological factors. For example, here the larval is, in addition to the baseline, is driven by rainfall and density dependence, and they can also have random effects on cluster and so on. Importantly, these parameters, they can also be impacted by the bed net, so which is the actual goal of this whole project, which is to quantify the impact of the PPF nets on each of these on these rates. And then another important thing to note is that in red here in the stages are the data that's available. So we have a data set that includes all adults. So it's count of adults that were collected. And within those, we have a subset that were kind of defined through the different stages of adulthood. So they could be not gravid yet, they were gravid, they were blood fed, and so on. So this is part of the observation process that feeds into the model. So like all mosquitoes are defined through a Poisson process. that's weighted by the proportion of the population that we are capturing, the number of traps deployed, the proportion of that particular species that we are interested in, and so on. While these partial data sets, they are all driven by binomial processes. So after the observation process, it feeds into the biological process. But of course, the tricky part in these models is always the parameterization and allocation of priors. And for that, we had to take a few different approaches. The first approach was what we call a meta model. And this is because the lowest time resolution we could use for this model because of the data was weak. But many of our stages actually lasted less than a week. They could be a day or 2 days or 3 days, and they're actually nonlinear. So we developed a meta model to parameterize the update equation. So what defines what leaves one stage and goes to another, and so on. So this meta model was a simulation of the life cycle that was done in half days for over a week. And this allows us to quantify the proportion of individuals that move from one stage to the next, and then we can use the GLM the GLM composition as a whole prior, the whole equation as a prior for these update equation rates. The remaining priors, some were a bit easier. So a lot of the values came from the literature and they're quite informative. So for example, we do know that mosquitoes lay between 50 and 200 eggs per oviposition, which happens every 2 or 3 days. And for the intervention, they were more uninformative. So they were quite broad priors, but they were strictly positive because we know that they can only reduce the population. And finally, the last tweak to this model was that we had to do some model selection, and we did this based on DIC. And first, we had to do model selection, unfortunately, for the density dependence parameter, which is highly dependent or highly linked to our catchability rate, so the proportion of the mosquitoes that we catch. And because there's no priors available for each, for neither of these two parameters. And we can't put an uninformative prior because we actually had no data for the larvae, and the density dependence acts on the larvae. So this made things quite complicated. So what we did was we tested a range of very kind of restrict priors, and we looked at model convergence and goodness of fit and the lowest DIC to kind of choose a prior for the density dependence baseline. And then the other model selection bit that we used was that we had to investigate the impact of intervention in each of the life history parameters here. And we tested one at a time independent, or we tested the impact on each life history parameter separately, or two at the same time, but they couldn't be consecutive. And this is because it creates a lot of confounding effects if you have the impact on consecutive life history parameters. So after all this, we actually managed to capture the population dynamics quite well. The model fitted really well to our data, which you can see here on the left-hand plot with the data in black and the prediction in blue. And here on the right, you have the estimated population density, and you can see that the peaks with the new net, with the PPF net in red, are slightly lower than with the gray, and overall we estimated an overall reduction of 9% in population size. However, once we start to distill these impacts and look at the percentage reduction in adult population, we see that all this impact was mostly from year 1. And this is because it seems that the second compound is quite volatile, so it just disappears from the net. So it's actually quite reassuring that we managed to capture kind of a switch in this, because by year 2 there was much less compound in the net, so it's quite interesting. But importantly, we were able to quantify the impact on the life history parameters, and the best model was one that retained the PPF impact on both adult and larval survival. but only the larval survival was distinguishable with about 3% reduction in larval survival, which, as we saw, can have important consequences for the population. So decreased larval survival was one of the proposed modes of action for this bed net, but the magnitude that we found is too low to be cost effective. So finally, I just want to conclude by saying that the application of these types of statistical models is not easy in ecology, but is very, very promising. We show that these PPF nets have the potential to reduce vector population, but they require the chemicals to be much more stable on the net. And because it reduces larval survival, we can combine with other interventions targeting other life history parameters if we want to maximize vector control. State space models can really reveal these hidden patterns in mechanisms, but some of the regulatory processes such as density dependence are still quite difficult to pinpoint with the data that's available. So if we could start kind of expanding the range of data that we collect, that would be amazing. And we are starting to do that, but it's complicated to kind of match larvae with adults in the field. But regardless, I just want to say that it's very clear that using these kind of statistical modeling approaches to guide public health decision making could really be an incredible, powerful tool that remains largely unexplored. And with that, I'm over my time. I'm really sorry. I will leave you with the list of acknowledgements of collaborations and, of course, funders, and thank you for listening.
Okay, thank you very much, Mafalda, for this very interesting presentation. So now the questions or comments, please. So I think there are no questions. So let's thank again Mafalda. Thank you very much for your talk. Thank you. And now we can move on to the last talk. So our last speaker is Maria Evitable Models from CAU, the Center of Statistics and Applications, and an emeritus professor of the University of Lisbon. And she will talk about statistical extreme value theory and applications, an appealing and challenging topic. Please, Yvette, thank you very much.
Please turn on your microphone. Your micro isn't working. It's off.
Ainda está sem som, Ivete, ainda está sem som. Ainda não conseguimos ouvi-la. No canto inferior esquerdo, tem que ativar o som, por favor.
Tá.
Okay.
Já está.
Okay.
Obrigada.
Apologies.
No problem.
Okay, now I cannot move this. Okay. Good afternoon. And first of all, I would like to thank the organizers of this event. Now you are listening to me? Yes. I
Yes,
also would like to thank Ana Cristina for this invitation. My talk is going to be very general. I'm going to speak about statistical extreme value theory, which I consider an appealing and challenging topic. And I'll stay essentially in the field of univariate statistics of extremes. And you have already seen a lot about multivariate extremes and spatial extremes. Anyway, so a brief outline of the talk. So extreme value theory helps us to control potential disastrous occurrences like floods, fires, hurricanes, and other extreme events. And the statistical extreme value theory is today faced with many challenges, especially the ones related to topics like risk modeling of big data and robustness of the methodologies that enable to understand the complexity of extreme events in the most diverse areas. Apart from the estimation of the extreme value index, the reliable estimation of other parameters of extreme events like the value at risk is also crucial for an adequate and reliable risk assessment. Recently, generalized means have been used with success in the estimation of the positive extreme value index and of value at risk, and can be used in the estimation of several other parameters of extreme events. In this presentation, emphasis will be given to the use of those generalized means and to the possibility of further using the PORT methodology, with PORT standing not for Portuguese, but for peaks over a random threshold. So let's begin with a brief introduction. So in the field of extreme value theory and more generally in almost all areas of statistics, the ordering of the available sample is of primordial importance. Such an importance enables us to have access to a broad statistical methodology and associated distributional theory related to ordered samples, as can be seen in several books on order statistics and extreme order statistics, among which I mention only the book by Arnold Balakrishnan and Nagaraja. There exists on one side a natural interest by ordering. Indeed, extreme values are important as an expression of the worst or the best that one can find in a sample, like minimal temperatures, high levels of dams, minimal lifetimes in reliability theory, and alternatively, a set of observations can be deliberately ordered to facilitate the statistical analysis we want to perform. Extreme value theory and statistics of extremes help us to control disastrous events of high relevance to society and with a high social impact. And the domains of application of extreme value theory are quite diverse. And I mention here a few. Among them, maybe I mentioned dynamical systems, and I referred a couple Freitas and Freitas, as was mentioned in the, I think, second talk, but also environment, finance, and insurance, among other topics. So earthquakes, fires, floods, and other extreme events have provided impetus for several recent redevelopments of extreme value analysis, of statistics of univariate extremes, and also multivariate and spatial extremes, partially due to the fact that rare events can have catastrophic consequences for human activities through their impact on constructed environment, essentially on constructed environments. By the late 70s, when I began research in the field of extreme value theory, it was common to work in the field of parametric statistics of extremes. In the 80s, there has been a shift towards semi-parametric or even non-parametric approaches, but I believe that parametric modeling, essentially based on probabilistic asymptotic results, is becoming again quite popular, particularly in spatial applications of extreme value theory. And apart from the estimation of the extreme value index, one of the primary parameters in extreme value analysis, the reliable estimation of other important parameters of rare events like the return period of high level will be among the topics to be briefly addressed. As mentioned above, we shall emphasize the use of generalized means and the possibility of further using the peaks over random threshold methodology coined and introduced in this paper. Indeed, the idea was of Paulo Araújo Santos, a PhD student of Isabel, and I like the idea very much because of PORT, as I told before, looks much like Portugal or Portuguese. And indeed, there is a very large community of extremists in an extreme area of Europe, which is Portugal, as I used to say. I have here further motivation for the need of extreme value theory, but maybe the audience doesn't need it. So to motivate the interest for this area and among a great variety of disasters that have happened recently, and even today I heard about Germany and what's happening there with terrible floods in the northwest of Germany. But I put here just two examples. So a reasonably recent one. It's not already so recent, but the floods in China and eastern Jiangsu in July 2020. These floods have deeply affected almost 25 million people, and rising waters across central and eastern China have caused the deaths of more than 150 people. And the historical floods in the North Sea in February 1953, something that I consider maybe as a big reason for the big development of extremes, particularly in the Netherlands. Then the level of the water exceeded 5.6 meters above the sea level. The maritime defenses were destroyed, provoking flooding in Holland, England, Belgium, Denmark, France, with the deaths of around 2,500 people. I put here two pictures. In the left, we have a flooded area near Yangtze River in Zhejiang, and the picture in the right is related to the North Sea floods. And as a consequence of the North Sea floods, as most of you know, the Dutch government formed the so-called Delta Committee, a very relevant committee which still exists, and it was decided that dams need to be built in such a way that the probability of a flood in a certain year should be 1 out of 10,000. But data have been observed during a much shorter period. It is thus necessary to extrapolate beyond observed data, either univariate or multivariate, dependent or not on time and or space. And on the basis of the so-called return period of an extreme event, extreme value theory can provide reliable answers on the height of such dam. Unfortunately, not always taken into account due to costs. And such a return period is merely the mean time interval between consecutive occurrences of a certain extreme event, like, for instance, the flood in the North Sea. Now we have spoken about sample data x1, x2, xn. So this is the terminology I use here, is associated with observed values from a random variable capital X, and they are typically used to study the properties of the cumulative distribution function underlying the data, which is defined as the probability that the random variable f of x is the probability that the random variable is smaller than or equal to x, or the associated quantile function, which is just the generalized inverse function of f. The quantile function at q is usually defined as the generalized inverse function of f of q, of f at q, for q in between 0 and 1. And when we think, for instance, on the usual statistical counterpart of f of x, which is just the empirical distribution function based on the order statistics, xin are the ascending order statistics associated to our sample, we just have, so 0 if x is smaller than the minimum, and 1 if x is greater than or equal to the maximum, and I over n in between xin and xi plus 1 n. In extreme value theory, we often want ops. We often want to estimate we often want to estimate the exceedance probability of high level x, which is usually greater than x and n. So we want to estimate this p, which is just 1 minus f of x. And then the empirical cumulative distribution function does not provide any useful information. It just provides the value 0. I put here the main points to be taken into account are essentially the following ones. Risk events are in the tails of the underlying distribution, and there are usually only a few observations in those tails, and is illustrated here in this figure. So you have the minimum, the maximum, and we often want to extrapolate above the maximum and below the minimum. Given the data I put here before, which look quite like a normal distribution, we could indeed try to associate a normal model to the data and to use such model to estimate tail probabilities. Then we would have a value different from 0. But the associated problems are essentially the following ones. So such a fitting is essentially ruled by the central observations, and the different models that fit the body of the data can lead to different tail extrapolations. And if our interest lies in the tails, with this I mean large or small values of X, why compromising the tail fitting? I put the question here, why compromising the tail fitting, forcing simultaneously the fitting of the body of the data? But this is a question that, it's a philosophical question that would give rise to a 1 hour talk or more than 1 hour talk, because, okay, some people are for the fitting of the body together with the fitting of the tail. Or most people are for the fitting of the body together with the fitting of the tail. But anyway, we need to consider models for the tails, usually based on asymptotic results. We can obviously put the question that I put here: is it sensible to use those models in all real situations which deal with extreme events? And again, I'm citing George Box and Norman Draper in their book on empirical model building and response surfaces. So we cannot forget that all models are wrong, but some models are useful. In statistical data analysis, extremes are often wrongly identified as outliers, being sometimes even ignored in the subsequent statistical study, given the fact that they are a long way from the fitted model. If our objective is to infer on day-to-day events, it can be relevant to suppress those tail data. But if our fulcral question is related to those tail events, which do not occur often, it seems sensible to apply the extreme value theory framework, giving particular emphasis to those extreme values. Extreme value theory is just a probabilistic branch supporting statistics, which deals with those situations, helping to describe and quantify the so-called rare events and extrapolating beyond the sample. Observations in the tail, as I mentioned before, are scarce, even when dealing with big data, and estimation above or beyond the sample extremes is often required. When we put the question, is there a hidden pattern underlying this type of extreme events? I think that most of the audience gets to know. The answer is positive, and such hidden pattern is next partially and briefly provided. And for that, I'm going to speak about a brief touch on asymptotic distributional theory of order statistics. It's really a brief touch. So a few asymptotic results useful in statistics of univariate extremes. Some of the key tools that have led to the way statistical extreme value theory has been exploded in the last decades are, in my opinion, and in the opinion of most people, the key result obtained by Fréchet on the functional equation of stability for maxima. That give rise to the now called Fréchet law. Indeed, he had just a very simple idea. So the maximum of maxima is still a maximum. Okay, something like this. And so you got a functional equation, and such a functional equation was later solved still with some restrictions by Fisher and Tippett in 1928. Who derived the possible non-degenerate limiting loss of the linear normalized sample maxima associated with an independent, identically distributed random sample, x1, x2, xn. And with this, I mean the non-degenerate limiting random, the limiting behavior of this xnn minus bn over n, where xnn denotes the maximum of x1, x2, xn, and then derived to the extreme value cumulative distribution functions, sometimes called of type 1, type 2, type 3, or Gumbel-Fréchet-Weibull, which is just a double exponential for the Gumbel, a Paretian tail of the type 1 minus x to the power minus alpha for the Fréchet, and a light tail with the finite right endpoint, a Max-Weibull. So such a result was initially formalized by Gnadienko in his 1943 paper, later by Lawrence Yan in his PhD thesis, and used by Gumbel for applications of extreme value theory in engineering and hydrology. Statistics of extremes, of univariate extremes, is thus mainly based on the so-called max table laws related to the non-degenerate limiting behavior of the sequence of normalized maximum values. And consequently, statistics of univariate extremes deals essentially with the above mentioned extreme value cumulative distribution function, so the Fréchet, the Gumbel, and the Maxwell, and the general extreme value distribution function, which can be written in this way and depends on this psi, which is the extreme value index, the primary parameter of in statistics of univariate extremes that measures the heaviness of the right tail function f bar equal 1 minus f of x. So the GEV, the general extreme value distribution unified form, was initially provided by von Mises in 36, then by Jenkinson in 55, and sometimes it's also called von Mises-Jenkinson distribution. And the heavier the right tail, the larger is psi. So we have Maxwell models correspond to psi negative, and we have a short height tail function with a finite right endpoint. For psi equal to 0, we get the so-called Gumbel cumulative distribution function for maxima and an exponential height tail function. And Fréchet height tail functions are heavy of a Pareto type with an infinite right endpoint and correspond to psi positive. I put here again one of the pictures, so where I put also the normal, apart from the generalized extreme value for psi equal 0.75. Look here at the tail, so quite heavy tail. Then G naught, the Gumbel, so an exponential tail, okay, the figure went again, double exponential tail, so which is equivalent to an exponential tail. Here I have the normal, a quadratic exponential tail, much heavier than even the Gumbel, and then a light tail with for a Maxwell with a finite right endpoint. So the aforementioned theoretical result is known as Fisher-Tippett-Gomdenko's theorem, also called extremal types theorem. And this extremal types theorem does a role similar to the central limit theorem for averages or sums, where the normal comes as one of the most, let's say, relevant between commas models when we have finite variance. The cumulative distribution function f is then said to belong to the max domain of attraction of the general extreme value distribution, and we use this notation. F is in the domain of attraction for maxima of GEV with an index psi. But statistics of univariate extremes deals also with extremal processes and the so-called multivariate extremal model related to joint limiting behavior of upper order statistics used. I put here this seminal paper by Ishai Weissman in 78, and also my PhD thesis is also in 78, and another paper in this book on statistical distributions in scientific world, among statistical distributions in scientific world, among other articles. Moreover, statistics of univariate extremes deals also with the generalized Pareto model, which is just 1 minus log plus log of the GV. So the GP is 1 plus log of the GV, and indeed as derived almost simultaneously in this paper by Balkim and Diane, and this other paper by Pickens. For a high U, it was shown that the conditional excesses, so given that X is greater than U, the excesses are well approximated by a generalized Pareto with an extreme value psi and with a certain variance sigma dependent on U. I put here also a bit on multivariate extremes, but just a bit. So the road from univariate to multivariate extremes is confronted from the very beginning with a problem. There is not a single way of toward the multivariate distributions. So different categories of order relations for multivariate data are of potential use, can be of potential use, and can be found, for instance, in this paper in the applied statistics by Vic Barnett. But the most useful order relation in multivariate extreme value theory is a specific case of what is called marginal ordering. So in the marginal ordering, so you have a vector of d-dimensional observations, xi1, xid, and the sample maximum, I put here this mn, is just, oh my gosh, is just the components of Mn are just so the component was maxima. So Mnj is the maximum of xij from I equal to 1 until n, and for j equal 1 to d. So this situation observed that the sample maximum needs not to be a sample point. So the definition might seem a bit artificially, contrary, for instance, to the definition of concomitance of order statistics, which lead to another multivariate, to other multivariate models. But still from its study, a rich theory emanates and leads to several statistical tools for analyzing extremes of multivariate data, most of the time is based on multivariate max stable models. And we have heard about multivariate max stable model, in that case only bivariate by Miguel, who showed the logistic model. But apart from the logistic model, we have a lot of multivariate max stable models. And for the details, I put here just these two books, the book by Berland, Cogber, Seeger, and Tegels, and the book by Laurentienne and Dana Freire, among other books and articles. More general framework, statistical applications of extreme value in theory have given emphasis to the relaxation of the independence condition and of homoscedasticity. It's always a bit difficult for me to pronounce this word, homoscedasticity, to the consideration of multidimensional and spatial frameworks, and from a theoretical point of view to a deeper and deeper use of regular variation and point processes. I have a bit on parametrics too, but maybe I just skip most of these things. I put here a few parameters of extreme events, but I think that it's not relevant to speak about all these parameters because I'm not going to use them. I'm just going to use maybe the return. No, I have an example with the return level of the value t, which is just the reciprocal tail quantile function or the generalized inverse function of f at 1 minus 1 over t, and the return period of a certain level. I give an example, just a very simple example in the field of statistics of univariate extremes to show the difference between the normal and the Gumbel, despite of both not rejected as possible models of a certain univariate set of data. And the return period of the level U can be written as 1 over 1 minus f of u. So the mean number of exceedance of u in an IID framework. I put here also the quantiles, but I'm not going to use the quantile estimation, so I'll just skip and go to Gumbel's approach of block maximum method, which is one of the most common methods in statistics of univariate extremes. It's obvious that statistical inference about rare events is linked to observations which are extremes in some sense, and different ways to define extreme observations lead to different approaches to statistics of univariate extremes. Sometimes only yearly or block maximum are available. It is then sensible to use the main limiting result in extreme value theory, which provides the max stable extreme value cumulative distribution functions as the unique possible limiting cumulative distribution function of the linearly normalized maxima. More generally, if we are interested, for instance, in floods or in drafts of a river in a certain place, it looks sensible to work with annual maxima or minima, even if we have access to all the charges. In the block maximum method, we obviously have identification of f to the power n, which is the distribution function of the maximum in an IID case, with the general extreme value distribution with a certain extreme value index psi, and scale and location parameters, which I denote here by lambda and delta, which replace in a certain sense the attraction coefficients that we initially considered to get a non-degenerate limiting distribution to the normalized maxima. So all statistical inference is then associated with extreme value or general extreme value models. And I put here an example just to show the difference in the estimation of return periods, for instance, or I think I put only return periods, maybe I put a bit more than that. When we have, for instance, data like we have here, we have access only to the yearly maximum discharges of this river in the Netherlands, in cubic meter by second, sorry. Whoops. And these data are available in the site related to the book by Byron Kober, Sigurds and Tegels. When we think on the box and whiskers plot, we have a figure like this one, okay? So indeed, this suggests a certain asymmetry. But maybe even a normal distribution can be fitted to this data, despite of those fellows there on the right. However, given the nature of the data, the right asymmetry and the importance of Gumbel's model in extreme value theory, it looks sensible to try the fitting of Gumbel's model to the yearly maximum, using then the block maximum methodology. However, I would like to say that the fitting of the normal to this yearly maximum would not be rejected by the usual goodness of fit parametric tests, and can be seen in our book, for instance, where we have used several packages in extremes. And when we think on a quantile plot, just linearization of the empirical distribution functions. So we plot the empirical quantiles versus in this case the empirical the general the quantiles of the Gumbel, and here the quantiles of the normal. So in those PQ plots, as you see, so the central observations are indeed quite well accommodated by the normal model. Only these tails are better accommodated by the Gumbel than by the normal. Indeed, when we fit a least squares line to the associated to the previous quantile plots, we get these estimates for the parameters mu and sigma in the normal model, and we get a correlation coefficient which is 0.9788. So a quite nice fit. I believe that you agree. And if we consider Gumbel least squares, the fitting of least squares, but associated to the Gumbel quantile plot, then we get a better, but not so much better. Okay, we get a correlation coefficient of 0.9925, slight higher than we got for the normal, but not much higher. However, if we try to use both the normal and the Gumbel to estimate, in this case I put here the t years return level. So for t equal 100 years, so if I'm estimating, so the average level of discharges overpassed by the yearly maximum every 100 years, I get, with the normal fitting, I get this value, 2778, okay, let's round to decimal figures, 2778, and with the Gumbel model we get 3298. Okay, so much higher, much above the estimated level associated with the normal fitting, and much more reliable, in the sense that when we try confidence intervals, we get much shorter confidence intervals. Should we have thought on the return period of the level 3175, which is the maximum data available, we would get, for the normal fitting, we would get a return period of 866 years, and for a Gumbel fitting we get a return period of only 76 years. Okay, so much shorter now, much below the value associated with the normal fitting. So I put here other approaches, but I already referred them. So the multivariate extreme value model and the peaks over threshold approaches, where we consider the excesses and generalized Pareto model for those excesses. Now a bit on semi-parametric estimation. I hope to have still time. So more recently, all the models I have spoken about, and for the block maximum, the multivariate extreme value, and the peaks over threshold methodologies have been considered under a semi-parametric framework. There is then no fitting of an adequate parametric model. It is only assumed that F belongs to the domain of interaction of the general extreme value distribution with an extreme value index xi, xi being the unique parameter of extreme events to be initially estimated on the basis of a few upper observations according to an adequate methodology. It is common to consider the k upper observations. So we consider a threshold, let's say xn minus k, which is the n minus k's upper order observation, and then the observations above those threshold. And such a threshold, indeed, in most cases, needs to be an upper intermediate order statistic. And with this, I mean that k needs to go to infinity with n, but moderately, so that k over n goes to 0 when n goes to infinity. I am again using the same notation, I for f minus 1 for the generalized inverse function, and u for the right-tailed quantile function. And I am here considering only Avital models. And those Avital models are models, I put here first the definition of the definition of the class of regular varying functions at infinity with an index of regular variation equal to a certain beta, which are just given by this equation here. And then a model, Avital model is a model with a tail f bar, which is of regular variation with an index of regular variation minus 1 over xi, or equivalently, the reciprocal tail quantile function is of regular variation with an index of regular variation xi. And I shall work, as I told you before, with the dm plus, so the domain of attraction for maximum of a general extreme value distribution with a xi positive. For those models, xi positive, we have a classical estimator, semi-parametric estimator of the extreme value index, which is the yield estimator. And the yield estimator is just the average of I, the average of the log excesses, okay? And this happens because the log excesses, the k log excesses are approximately the k order statistics of a sample of size k for an exponential model with mean value xi. And so we have the average for the estimation of xi. So here I'll refer only one of the competitive generalizations of the Hill estimator. There are many competitive generalizations of the Hill estimator. I refer only one. This one is based on the fact that the Hill and due to the properties of the logarithm can be written as the logarithm of the mean, the geometric mean, or the mean of order 0 of these quotients of order statistics, which I denote by UIK. And so rather than the power mean of order 0, we can consider the power mean of order p, okay? And this was this power mean of order p was first considered for a p greater than or equal to 0, almost simultaneously in 3 papers. In these 3 papers I put here, and later in 2016 for any real p in this paper published in the journal Extremes. So we just consider the mean of order p of those statistics yk, okay, which are defined here for p equal to 0 and for p different from p, okay, for the general p real. And we can then consider the class of mean of order p extreme value index estimators, which are given by this functional expression. These estimators are consistent, or the consistency was shown only for p smaller than 1 over xi, and asymptotic normality was initially shown for p smaller than 1 over 2 xi. Recently, in this preprint, we have considered what we call the non-regular framework, so p greater than or equal to 1 over 2 xi. And some results have been developed. So what happens is that the use of this extra tuning parameter and the min for the P methodology can provide a much more adequate and reliable estimation of the extreme value index. Asymptotic normality is achieved for P smaller than or equal to 1 over 2 psi. But we can know up to P equal 1 over psi, getting then a sum stable behavior with an index of sum stability equal 1 over P psi. And for P equal 1 over psi, we get for HP of K minus psi a deterministic dominant component of the order of 1 of log of K. Okay, and that provides an almost a non-degenerate behavior for this random variable. The challenge is obviously not to go beyond P equal 1 over psi, but several algorithms, which will not be discussed here, have been conceived so in order to perform such a goal. Now the port, as I said that I would say a bit about the port extreme value index estimators. All the aforementioned extreme value index estimators depend on this tuning parameter, are highly flexible, as I said, and as often desired, and contrary to the extreme value index itself, they are not location invariant, depending strongly on possible shifts in the model underlying the data. So it is thus sensible to consider the use of the port HP estimators. They are similar in spirit to the port H estimators, which were studied in this paper I mentioned before, and also in this other paper in the Communication in Statistics, among other articles. And what happens is just that rather than the original sample Xn, we consider a sample of excesses over usually an intermediate, or generally we can consider any intermediate order statistic, but we can go up to the minimum only if the underlying model has a finite left-hand point, okay? And so the port HP class of extreme value index estimators has the same functional form of the HP, but with the sample Xn replaced, oops, I cannot touch, the sample Xn replaced by the sample of excess, XNS. Okay, so we have here the functional form, HP of Kx equal HP of K, based on the sample of the excesses. Okay. I still put here a stream parametric estimation of other parameters of, we can, similarly to the estimation of the extreme value index, we can then estimate the return periods, exceedance probabilities, tail dependence coefficient, Weibull tail coefficient, I quantiles, the so-called value at risk in insurance, finance, and so on. And just as we did before, so we base inference on the large K order statistics, and usually in supermetric estimation of any parameter of extreme events, we need often to assume that K is intermediate and sometimes a bit more than that, but I will not go into detail. We can also apply the port methodology, an adequate port methodology to the estimation of other parameters of extreme events. And usually we are led to no change in the asymptotic variance. We just change the asymptotic bias, but that can be nice because these estimators sometimes have a strong bias. Wait. It seems that I have no more slides. Now I have. So we have here paid attention essentially to the univariate case, but extreme value theory is also of high relevance both in the multivariate and in the spatial setups whenever dealing with the modeling of extreme events, or equivalently the modeling of risk. Oh, I think I had some overall conclusions and I skipped the overall conclusions. Maybe I still have time, Christina, or no? I still have time to draw some overall conclusions. I believe that statistics of the extremes, univariate extremes, is still a quite challenging topic of high relevance in risk modeling. Important developments have appeared recently in the area of spatial extremes, where parametric models, both asymptotic and pre-asymptotic, became again quite relevant. And in a semi-parametric framework, topics like threshold selection and the port methodology are still challenging. The use of this extra tuning parameter and the mean of order P methodology can also provide a much more reliable estimation, and other generalizations of the mean can be considered. Risk analysis related to extreme events are challenging, require the combined expertise of statisticians and domain experts in different areas like climatology, hydrology, finance, insurance, and so on. And the related statistical research with critical risk assessment can be found in the books of Embrecht, Kluckenberg, and Mikosch, and in the books already referred by Byron Tendal and myself and all, and also in a more recent book of Deepak Day and Diane. We, as I skipped and I put this, we have here paid attention essential to the univariate, but extreme value is of high relevance, both in multivariate and spatial setups, whenever dealing with the modeling of extreme events, or equivalently, the modeling of risk. So, put again a sentence, we hope to have increased or sparked, if there are people who have never heard of it, they are interested by the field, which is relatively recent from an historical point of view, but still with a lot of applications, so many as we can conceive. That's all. Thanks.
Okay, thank you very much.
I have references at the bottom, but I think this is afterwards accessible to people, no? And that's all.
Thank you very much, Yvette, for this very nice talk. So now we have time for questions. So you can write them in the Q&A button, please. I think we have a question from Livia, but I cannot give permission for him to talk. Right, Luis?
No, he can talk. He can talk. He passed to our side.
Okay.
And he can talk.
Okay.
May I talk?
Yeah.
Yeah. Olivier.
Olivier, sorry.
Yeah, no problem, no problem. First of all, my congratulations for Yvette. It was an impressive talk. And just a short question, the equivalence between the application in risk assessment or extreme value situation. Are there a lot of applications already in a risk assessment? I don't know if you hear.
I believe there are already a lot of applications in risk assessment. I cannot give you exactly, but for instance, if you have a look at that book of Deepak Day, that one of 2015, they have there several applications on risk assessment.
Thank you. It was very good. Thank you. Thank
You more questions, David, please?
Yes, Yvette, thank you very much for this very nice talk. So always inspiring. So I wanted to ask, actually, I transformed my comment in question before. So in your experience, we had this heat wave in Canada, and if you look at the average temperature over an area that covers Vancouver, Lytton, so it's quite a large area. You look at the daily temperature, and you see that these events hit at 5 sigma from the data that starts at 1948. So you talk about outliers and extreme events. So me as a physicist, if I get an experimental data that is 5 sigma, I say like, well, maybe this is an outlier, but this is not an outlier because clearly
we have to accommodate.
We have to accommodate. So it is interesting that if we compute the return time of this event actually without taking it into account, it's impossible. So the distribution is a viable with a certain shape, negative shape parameter. Then if we take into account this event, of course, it becomes possible, and the shape parameters almost become 0. So from negative, it goes to almost 0. Yeah. So what's going on? I mean, would you say that this is an event that belongs to the previous distribution, or it's a it's possible that it's a new state of the climate that we have to explore somehow, or we need different tools to study this?
Okay, I agree that okay, an extreme value index 0 may look a bit strange, and maybe we could go for those truncated Pareto models, which also have an extreme value index equal to 0, but they indeed fit quite well those very large values, you see. And so we just need to find a reliable estimate of the truncation point of that Pareto model, you see. And so from a theoretical point of view, we have xi equal to 0, limiting. Mm-hmm. But what happens is that indeed I spoke slightly about the pre-asymptotic behavior. And what happens is that when we think on the Gumbel as the limiting behavior of the normalized maximum, indeed we can have an asymptotic Gumbel behavior, but pre-asymptotic behaviors which look much more like either Weibull or Fréchet. Okay. Mm-hmm. Which are much closer. This comes from the paper of Fisher and Tippett, and I worked a lot about it in my thesis. And recently, a lot of people has been revisiting this kind of pre-asymptotic behavior. But the pre-asymptotic behavior, all the truncation of a Pareto model are, let's say, things that we can apply for that type of data. We have now in Vancouver and all the Western states, I think, isn't it? Because I have heard of 52 or something degrees in California a few days ago.
Yeah, no, thank you. Because one thing I want to say that in the extreme event attribution community, although people are aware of the work you did, you all, Philippe Navot and colleagues that you know very well and you work with, I mean, they are still using the standard GV to compute the, so maybe this is the revenge of mathematics or physics that we can observe these 5 sigma events from time to time.
You saw that I gave that simple example. Even the Gumbel has a reasonable tail, right tail, much heavier than the tail of the normal, which is just quadratic exponential, and so the normal can give rise to those plus minus 5 sigma, and that does not happen even with the Gumbel. But we need to go beyond the Gumbel.
Okay. Thank you. Thanks.
Thank you very much. Now we have a question from Miguel, please.
Yes, thank you very much, Yvette, for this excellent talk.
There's peanut for you.
Thank you so much. So I have a comment that is a comment curiosity. I'm taking the opportunity to ask you this, and it's also somewhat related with the comment that David was mentioning earlier. So in a world where extreme events may have a dynamical component guiding them over time, if we think of return periods from that point of view, what can we do, right? Because if we just get replacing the denominator f by time varying distribution function, the law of that f will be changing over time. And in practice, what we would like really to know, at least that's what I believe, would be really to be able to claim something about, okay, we've seen this event and it's very likely we won't be seeing something on the same scale again in the next 100 years, but keeping also the dynamics of that f into account. I mean, I'm just challenging you with
No, I agree. I agree with you. So it's the problem of homoscedasticity that we need to go to heteroscedasticity. Obviously, I agree with you.
Okay. So, thank you.
More questions? Okay, I think there are no more questions. So we thank again Yvette. Thank you very much. And I would like to thank again the four speakers, of course. Thank you very much. And I also would like to thank the audience for attending this session. Thank you very much. Okay, so can we finish the session, Luis?
Yes.
How we proceed?
Yes.
Okay.
No questions from you, Luis? No.
No. just how are you? Yeah.
So.
It's a private talk. What?
Thank you, everyone.
Goodbye.
Okay. Thank you, everyone.
Thank
you.
Thank you.
See you.
Thanks a lot. Thank you, Ana Cristina, for organizing.
Thank you.
Cheers. Bye-bye.
Bye-bye.
Bye.
Bye-bye.